I'd like to ask Dr. Croat to come up here, please. One of the greatest technologies that we're still feasting off of and only beginning to scratch the surface of is the incredible things that rare earths can do. From holmium lasers and lutetium detectors. One of the first really big uses for rare earths, besides phosphors and pitcher tubes and such, was invented by this humble man, a man who went to Ames, a Midwestern guy, and all he did was change the world. Invented a practical way. There were rare earth magnets back then, but they were exotic, samarium cobalt, and one of the things that Dr. Croat did when he got to General Motors Research Center was come up with a practical way to make neodymium iron boron magnets. There's a beautiful article that I have with you in it, and you're being interviewed. It's a Delco Remy newsletter. The most unbelievable thing in it is, do you think there's something besides starter motors that we could use these in? And he said, maybe hard drives, some other stuff. It's my honor to personally get to meet one of the guys who did one of the last great inventions of the United States here. So thank you very much.
Well, to start, I'd like to thank the Thorium Energy Alliance for this award. I'm honored by it. I find that I am in total agreement with their attempts to change policy relating to both rare earths and nuclear power policy, and I wish them the very best going forward in the future in this regard. I also want to thank Vicki Bruce for putting me in her book. Again, I agree completely with her in her attempts to highlight the deindustrialization of the United States and loss of our manufacturing base. I hope that books like that can turn this around and do something about it. And finally, just a word about the conference itself. I found it very interesting. It was wonderful to be here with so many very intelligent people, but also people that are like-minded, which I usually don't find in most places in the world. So I appreciate being here, and I thank you all for being here today to honor me with your presence while I receive this prize. Thank you. So now turning to my talk, and basically it's about the discovery of neodymium iron boron. And of course, neodymium is one of the rare earths, one of the light rare earths. I'm going to talk about why did we need this magnet and what did we do in terms of the research going forward to discover this magnet. To begin, I was introduced to the interesting and wonderful world of rare earths at the Ames Laboratory, Iowa State University, where I did my graduate work in the Department of Metallurgy. I might point out that the Ames Laboratory during the Second World War was part of the chemistry division of the Manhattan Project. It was headed by a man by the name of Dr. Frank Spedding, who was anybody that knows about rare earths or has studied rare earths knows he's one of the very important figures in the rare earth industry, and in fact was referred to often as the father of rare earths. During the Second World War, the Manhattan Project worked primarily on the chemistry of uranium and plutonium, and in fact they developed a technology for producing metallic uranium and plutonium, which of course went into the bombs. They also, interestingly enough, provided roughly half of the uranium metal for the first controlled fission reactor at the University of Chicago, which took place on December 2nd, 1942. And in fact, Dr. Spedding was there with Enrico Fermi and the other luminaries of that time during that particular event. Following the Second World War, the Ames Laboratory became part of the Atomic Energy Commission. And at that time, shortly after the Second World War, Dr. Spedding invented the thing that he is most famous for, which is the ion exchange process for the separation of rare earths. Again, anybody that knows much about the rare earths knows that they're intimately mixed together, their chemical properties are very similar, and they're very difficult to separate. So because of this invention, basically the Ames Laboratory became a major center, in fact, basically the only center in the world that was doing significant amounts of rare earth research and development. They basically were the only place in the world where you could find large quantities of research grade rare earth metals. I obtained my PhD in metallurgy there. My thesis was on the preparation and magnetic properties of rare earth, very high purity rare earth metals. So I became somewhat of an authority on rare earths. My major advisor was in fact Dr. Spedding. I was his last PhD student just before he retired. I was the last of several hundred PhD students in what he called his family tree. While I was doing my research work, I was very worried about getting a job after I got out of college, because the rare earth field the rare earth industry at that time was so small. There was no use for these things. I thought that it'd be very difficult to get a job. But immediately after getting my PhD degree in metallurgy, I was hired by the Magnetic Materials Group Physics Department at the General Motors Research Laboratory, which was located in Warren, Michigan. It's a very lovely laboratory. And the first question you might ask is, why was General Motors interested in permanent magnets? And the answer to that is, in the 1970s, General Motors was by far the world's largest automotive company producer. And automobiles are by far, and again I'm saying by far, the largest user of permanent magnets in the world. They're used in all of these applications that you see are highlighted here on this car, and in addition to some others. In fact, a luxury car today, the two front seats might have as many as 12 motors to adjust various things on your seat. Most of these applications were motors. They're DC brush type motors at that time, and still today. Most of them use a rather inexpensive magnet called a ceramic or ferrite magnet. Right after I arrived at the research labs, the first OPEC oil embargo had occurred in 1973, and the price of gasoline in the United States soared and around the world. Therefore, there was an intense effort on the part of General Motors and other automotive manufacturers to improve fuel economy of the automobile. And one way, of course, to improve fuel economy is to reduce the weight of the car. And one way to do that is to reduce the weight and size of all these components on the car, these motors. And in fact, there's a compounding effect. If you reduce the weight or the size of a window lift motor, you might be able to reduce the size and the weight of the thing that holds the subcomponent that holds the motor. And in addition, maybe you can make the door thinner and lighter. So there was a compounding effect. At that time, samarium cobalt permanent magnets had actually been invented, but they were considered far too expensive for use in high volume automotive use, since samarium is relatively rare and expensive and cobalt is very expensive. So the mission of the Magnetic Materials Group was basically to develop a lower cost, higher performance rare earth iron permanent magnet to replace the cobalt. However, there was a serious technical problem in developing a rare earth iron permanent magnet that had bedeviled material scientists that had been working on this problem for several decades. And the problem was the lack of a suitable intermetallic compound. And basically, material science research in the permanent magnet area is a search for intermetallic compounds, good intermetallic compounds. There are a number of requirements for this intermetallic compound. First, it has to be ferromagnetic. It has to be magnetically ordered. But it also has to have a uniaxial crystal symmetry. This means that the C-axis, or one of the axes in the crystal, must be longer or have a different energy level than the axis in the basal plane. This means that the C-axis has to be at a different energy level than the A and B axis in the basal plane. The material has to be hexagonal, tetragonal, or rhombohedral, which means that you could not use a cubic material. And a lot of intermetallic compounds are cubic because all three axes are the same. This means that you don't have any difference in energy between the three axes, so you don't get any coercive force in this kind of material. The other requirements are that it must have a reasonably high Curie temperature. In other words, it has to stay ferromagnetic to a fairly high temperature, because under the hood of a car, for example, it can get 180 degrees centigrade. And the third requirement is that to have an economically viable magnet, something that could be used in automobiles, you have to use one of the low-cost, abundant light rare earths, like praseodymium or neodymium. Praseodymium and neodymium are the third and fourth most abundant rare earths. Shown here is the composition of bastnasite ore, which is the ore that's obtained from the Bayan Obel mine in Inner Mongolia. This is the largest rare earth mine in the world. And you can see that neodymium has a composition of about 18.5% neodymium and about 6.2% praseodymium. On the other hand, samarium is only about 0.8%. That's why it's more scarce, therefore its price is higher, and that's why samarium cobalt magnets are so expensive. Now, the first thing you might ask is why not use the two most abundant rare earths, cerium and lanthanum? And the problem here is that the high coercivity in rare earth transition metal magnets results from the highly anisotropic shape of a 4F wave function in these rare earths. Lanthanum and cerium, unfortunately, have no 4F electrons, therefore they have no magnetocrystalline anisotropy, and therefore they have basically no coercivity. So basically you can't use cerium and lanthanum, the two most abundant, the two cheapest rare earths, in these rare earth iron permanent magnets. I might point out that these highly anisotropic 4F wave functions are the most interesting and most valuable properties of all rare earths. It's a thing that gives rare earths their most interesting properties and most technical applications. The problem with the rare earth iron binary systems is shown here, where I plotted all of the rare earths and the various intermetallic compounds that form, which includes the rare earth iron 2 compound, the rare earth iron 3 compound, the rare earth 6 iron 23 compound, and the rare earth 2 iron 17 compound. Two of these, the rare earth iron 2 and 623, are cubic, and they were not considered candidates for permanent magnet applications. And we can see that for praseodymium and neodymium, none of these compounds form except for the 217, and they unfortunately have very low Curie temperature, so they were not considered candidates for permanent magnet development. So at this time, and this had been the case for a couple of decades, there appeared to be no way to begin development of a rare earth iron permanent magnet. However, myself and a colleague one day saw this paper from the Applied Physics letter by Art Clark from the Naval Ordnance Laboratory. He annealed amorphous high-rate sputtered terbium iron 2, and he found that at about 350 degrees centigrade, the coercivity suddenly jumped up to a reasonably high value of about 3.5 kiloerstin. Extremely interesting because, first of all, this was the first time anybody had ever made a rare earth iron permanent magnet. It was also interesting because terbium iron 2 is a cubic material, and you shouldn't have been able to make it into a permanent magnet at all. So we believe that the coercivity of this material was due to the formation of a new magnetically hard, but a metastable phase, a non-equilibrium phase. It didn't crystallize into a cubic phase, it crystallized into something else. So this work became the genesis of a research project at the General Motors Research Lab to investigate the formation of metastable phases in rapidly solidified neodymium iron and praseodymium iron alloys. The rapid solidification technique that we began to investigate was called melt spinning. This was a relatively new technique at the time. It consisted of a process in which a molten alloy was pressurized and a stream of it was driven onto a rotating disc to form a rapidly solidified ribbon. And this is the first laboratory melt spinner that I had built. Again, you can see it's got a 6-inch diameter copper wheel. It's got a quartz crucible and an induction heater. It's capped, and there's pressurized argon used to drive the molten alloy onto this disc, which is rotated with this drive motor to produce this ribbon on the right-hand side of the crucible. Since these materials are highly reactive with oxygen, the whole thing has to be carried out inside a vacuum system. Late 1970s to early 1980s, I discovered that magnetically hard metastable phases readily formed in all of these materials when they were melt spun over a range of quench rate. In other words, when you change the quench rate and slow the quench rate down at a certain rate, these materials develop very high coercive force, in some cases as high as 20 kiloerstin. But the most important thing that I discovered is, like any material scientist, I started adding things to see if I could change the properties. I added this and that. And in the process of doing this and in the process of melt spinning these materials, I discovered the neodymium-2 iron-14 boron intermetallic compound. And this compound is really the major discovery. It's the basis of all neodymium iron boron permanent magnets. It had a very high Curie temperature. It had a crystal structure. It had very high magnetic strength, and it had a very high magnetocrystalline anisotropy. I might point out here also that a man in Japan discovered this same compound independently within a couple of months of when I did, but I actually think I beat him. I think he admits that. But we had some problems. The General Motors wasn't very fast getting to the patent office. And so we ended up with patents in the United States. He ended up with patents in Japan and Europe, and they fought for a number of years over this issue. And finally had to cross-license each other. And then in terms of commercial development, we very soon found that this rapidly solidified powder, when you ground it up, mixed it with epoxy, and made a very nice permanent magnet. And there was immediate interest in Delco-Remy, which is a sister division in Anderson, Indiana, that produced many of the motors in the cars that we saw earlier. They wanted to investigate whether or not these magnets could be used to reduce the weight and size of these motors, including cranking motors. And so the decision was made. There was also interest in the possibility of turning this into some kind of a business. So the decision was made to develop the production melt spinning process in Delco-Remy, Anderson, Indiana. And so we built this prototype melt spinner in late 1983, and during 1984 and 1985. It was a very trying development, but we finally developed the technology for producing this melt spun material in very high volume and very high quality. And we also developed the technology for producing the bonded magnets, which consisted of blending it with epoxy, compacting it in a press, curing the epoxy, spray coating it to protect it from particularly condensed moisture, and then you see the finished coated ring magnets. We started the commercial business, Magnequench. Magnet by rapid quenching. It's just an acronym derived from that sentence. We founded Magnequench in Anderson, Indiana in 1986. The first generation production melt spinner was installed at the new factory also in 1986, and the first sale of melt spun magnetic powder took place to Japanese companies, micromotor companies in 1987. Just to show you the very first applications for this material, on the left-hand side is a small micromotor that was used for the autofocus on both still and motion cameras. That's a US dime laying there next to it. And on the right-hand side is the read-write for the old floppy disk drive. Some of you are young enough to remember this. But that at one time, of course, was a major means of storing media in the world. It's now extinct, but at one time this took a considerable amount of this powder to make the magnets for these small motors. Today, of course, the application base is quite different, but again, most of the applications are ring magnets. They don't have to be. Some of them can be little square magnets. In fact, the magnet sensor on your airbags, the magnet in there is typically a bonded neodymium magnet. But today, the major applications are these ring magnets that go in spindle motors for hard disk drives and optical disk drives. The other major application are stepper motors that go into things like the paper feed for your printer and for scanners, and for medical technology. There's all sorts of things. The little louvers on your in-room air conditioners that adjust up and down, they use one of these motors. The thing that adjusts your mirrors on your car, on the out mirrors on your car. Unless you're very inactive, there's hardly a day could go by that you didn't use one of these magnets somewhere in your life. In terms of the commercial development of Magnequench, it coincided with the early development of the personal computer and all the peripherals that were needed with the personal computer. So between 1987 and 1995, there was a considerable increase in sales, and in fact, the future looked very bright. However, in 1995, GM suddenly announced they were selling Magnequench because it was not core to the automotive business. And to be quite fair to them, although neodymium iron boron was much cheaper than samarium cobalt 5 magnets, it was still a little too expensive, and they didn't think there were going to be much use for it on an automobile. And at that time, General Motors was having cash flow problems. They had one of their first major financial problems, and they needed money, so they started selling everything they could, and they ended up selling Magnequench. And the business was eventually sold to a group of investors, which included elements of the Chinese government, including the son-in-law of Deng Xiaoping. This sale has been mentioned here several times today, and Vicki Bruce covers it in her book, Sellout. But finally, the entire business and technology was transferred by the new owners they were required to keep it open for 5 years. But at the end of the 5 years, they immediately transferred the business to Tianjin, China in the year 2001. And of course, looking back on it, you have to ask, what did the United States get out of this? We got nothing but a loss of middle-class jobs, the deindustrialization of our economy, and a big trade deficit. I see nothing else we got out of it, so it's been a bad deal for us all around. Anyway, thank you very much. That's all I have to say.
Thank you so much, Doctor.
Sorry about that.
Now, don't you think Dr. Croat deserves $1 billion more than the inventors of WhatsApp?
Thank you.